Hello again, another week and another topic. Today we're going to be learning about object-oriented programming. Much like functions, we don't really need object-oriented programming, but sometimes it can make the program a little easier to read and nice and modular. So let's get into it. So first what we're going to do is we're going to talk about the concepts of classes and objects. This is something that students are often confused about at the very beginning, because they both seem to represent something quite similar. But generally speaking, this is something that everybody can get the hang of. Then what we're going to do is we're going to go on and talk about how you can implement classes in Python, including how to define member variables and functions. So in short, object-oriented programming revolves around the concept of a class. A class is a way for us to take things that are really closely related and put them together. Now, we have previously seen tuples and dictionaries that do that as well. So tuples and dictionaries allow us to take different data values and put them together if they're all related to the same concept. Classes allow you to do that one step farther. We aren't just able to collect data, we're able to collect functions as well. So the functions can operate on that data. They can provide relatively high-level functionality or really low-level functionality. They can perform background functionality like checking security parameters and so on. A class is a really nice way for you to put all of your code related to a concept together. So for instance, if I wanted to create a website where you could buy products like Amazon, I could make classes that represent products, orders, ordered items, customers, shipments, that kind of thing, would all have classes. And everything, all the functionality related to products would be placed in the products class. Okay. So first, let's just talk about object orientation conceptually. So a class, I like to think of a class as sort of like a cookie cutter. So that's the analogy that I use mentally. A class is a template that describes what an object is supposed to look like. So there are these two different concepts that you need to understand: classes and objects. So an object is a very concrete thing. So for example, if you have your phone right now, pick up your phone. Your phone is definitely an object. It's something tangible. Not all objects are tangible, but certainly tangible objects are objects. So your phone, I have a cup of tea here. That's certainly a tangible object. Those are all examples of objects. Classes are more abstract. And so when we think about classes, we talk about the things that objects of that sort have in common. So for example, I might define a class that defines what a phone is actually like. What kinds of features do we have in a phone? For example, all phones have like a processor, a system on a chip. They have RAM, they have a screen, they have Wi-Fi and other wireless connections. They have charging ports and all that stuff. This is the kind of thing that you could describe in a class, and the values of this data that you put in the class could make for different objects. So I can have one phone that has 8 gigabytes of RAM and another phone that has 6 gigabytes of RAM. And so the class just describes what the object generally looks like. What kinds of data do you store about that object? What kinds of functionality does it have? Okay. An example might be at a lower level in programming is a variable declaration. When I declare a variable, it tells you something about what I'm planning on putting into that variable. So this is not a great analogy for Python, unfortunately, because in Python, a variable is just kind of implicitly declared when I give it its first value. But in some programming languages, you declare a variable in advance. You might say something like int x. So I'm basically saying now there is a variable called x, which is going to be an int type, but it doesn't have a value yet. I'm just saying that there can be a value there. So I'm describing the nature of what the object's going to be without getting into the details of what the object turns out to be in the end. Okay, maybe that's complicated. So going back to the cookie cutter analogy to hopefully help you understand, a class is like a cookie cutter. If you buy a cookie cutter, say at the dollar store, shaped like a snowman, it means that you can make snowman-shaped cookies. The individual cookies that you make from the class are the objects. Okay, so you use the cookie cutter to make cookies. The cookie cutter is the template that describes what those cookies are supposed to look like. And the cookies themselves are the product as that result from you using that cookie cutter. Okay, so a class is actually a type. This is one of the more complex types that we alluded to earlier on, and we've talked about lists and dictionaries and tuples and strings, and now finally classes. This is the last of all the types that you can have in Python. But the power of a class is that you can define your own type that is completely customizable. So we've talked about the built-in types a fair bit, and we've said, okay, well, there are strings, and you can use the plus operator on two strings, and that concatenates them. And there are lists, and you can do the same thing. You can use the square bracket notation to get an individual element of a list, and so on. But these are defined as part of Python. If you want to define your own class, Python gives you the power to do that. And the advantage is, in Python, in fact, in most programming languages, when you define a class, you can add functionality to use those operators and that same functionality in a different way on this new kind of object that you're creating. So what does it mean to add two Amazon products together with the plus operator? I have no idea, but you could define a use of that operator that involves combining those two products together. Or maybe a more realistic example might be if you take an order object, which is some order class, and you add to that order a product instance, and then that'll add the product to the order. And then the order now will have that product as part of the order. So that's an example. So a class describes the nature of the type that you want. So imagine, for example, I want to make a game. So I want to have a player in the game. And maybe this is an RPG game, and I want the player to be able to have different kinds of armor that'll provide protection, different kinds of weapons that'll allow them to attack, etc. So if I'm defining my class that represents my player, or my player's inventory maybe, then I'll give it slots for things like weapons and armor. And I might put in some functionality as well, not just the data, but I'll put functionality that'll check to make sure that the stuff they're carrying isn't too heavy. So if I'm carrying like 12 sets of armor, all made out of iron, it's going to bog me down. I'm not going to be able to walk with all that weight. So I'm going to have some code in that class to check weight constraints. I might also have other things. So for example, if I want to put on a helmet, I might not be able to put on a helmet. Maybe the helmet's so heavy it's going to injure my neck because I'm, like an acrobat sort of character, and I'm really lean and really, I'm not particularly strong, but I'm very fast and nimble, and I'm great at jumping and flipping and so on. But if I put on a super heavy helmet, I could injure my neck. So in that case, there might be checks to make sure that I've met the sufficient minimum criteria in order to put this armor on. That's the kind of thing I could put in a class. So data, such as what kinds of objects am I carrying, and also functionality, such as am I carrying too much? That's the kind of thing that you'll have. So that's the advantage of a class, that we can put that functionality and that data together into a single unit. All right, so then contrast that with objects, which are really very concrete. So the idea of a laptop is something that you're familiar with. If I say, computer science students should have a laptop, you probably would agree. But I'm not specifically saying, computer science students should have this laptop. Here, come and get it. I'm saying, generally a laptop. And so that's a concept. That's an abstract concept that's describing what it is you need. On the other hand, an object is a real concrete thing. It's something, it may not be tangible. It may not be something that you can hold in your hand, but it is a very specific instance of the class. Okay, so we might have a class which has a player, but if it's a multiplayer game, I might have multiple instances of that same class. So each player that's playing on a different client, they might represent an instance of that class. Now, they all have the same type. They all have the same functionality. They all have the same data spaces, but the data that's in those data spaces might not be the same, such as describing the player's strength and the player's agility and so on. They might be different from player to player. But describing the class, such as I need a number that represents the strength and a number that represents the agility of the player, is what I'm going to put in the class. The objects are going to have filled in values for that data. Okay. So an example for a laptop might be a laptop that has 32 gigabytes of RAM and a 3.6 gigahertz CPU and a 3070 GPU. That's an example of a very specific laptop, maybe one that you're using, but a laptop in general doesn't need to have those exact same data values. And in fact, that laptop sounds a bit overkill for this class. All right. So an object-oriented programming is basically a program that's made up of instances of objects. So just to keep in mind, instances or objects. When I use the word instance, I'm usually talking about the exact same thing as an object. So an object is an instance of a class. So that's where that name comes from. So sometimes we'll refer to it as an object and sometimes we'll refer to it as an instance. We usually use the word instance when we're specifically talking about the object's relationship with the class that was used to create it. We'll use an object under normal circumstances. When we just have an instance of a class, we'll just call it an object typically. All right. So an object-oriented program is really just a bunch of objects, and those objects are going to talk to one another. And what that really means is they're going to be calling one another's functions. So we're going to have a starting point, maybe a main function, let's say, and that main function is going to call the other functions on the other objects. And objects can create instances of other objects, instances of classes, and that'll create other objects. So objects can create other objects using classes. And we'll talk about all of these things today. So what are some of the benefits? Well, actually, it's really nice because an object is just kind of a bigger module. So we have functions, which are really small. I mentioned that functions are usually less than 20 lines of code. And if you have a lot of functions that are 3, 4, 5, 6, 7, 8 lines, those are very easy to understand. You can actually look at the class and understand everything about look at the function, understand everything about what that function does. An object kind of does the same thing. Imagine I have a class, and that class defines maybe 5 functions. And even if I'm not looking at the source code of the functions, just based on the names of the functions, I understand what 5 functions or which functionality is available on instances of that class. So I could kind of understand at a higher level what's going on in a class at a time. If I have a class that has hundreds of methods or hundreds of functions in it, it's actually not going to be possible for me to understand it. But if I only have 5 or 6 functions in that class, then I can. So that's one advantage. Another advantage is that the class can hide the data. So I mentioned that classes have data and functionality. What we can do is we can hide the data. So this is called information hiding. And it's actually a big advantage because rather than working with the data directly, we have these functions that allow us to manipulate a data in a very controlled way. So when we have a date, for example, I want to set the date of a particular order. And what am I using internally to store that? Am I using milliseconds since January 1st, 1970, or am I using a string representing the date? So there's different ways of representing that date. And if I change at a later time what representation I want to use, and I'm working with that data directly, that means that every part of the program that deals with that data directly needs to be modified. And that could be really inconvenient. So that information hiding is very powerful because if I ever want to change the internal representation of some data, all I need to do is change the functionality in the class itself. Everybody else in the program still uses it the same way that they always have through these functions. Another feature that object orientation provides is encapsulation. So encapsulation is just bringing everything together. So before we had dictionaries and we had tuples, and that's putting all the data that's related to a concept together. But now we also have the behavior related to that concept, which is actually quite powerful in terms of debugging. So if I have a program and something's going wrong with how orders are being processed, there's a pretty good chance that it's somewhere in the order class where that error is happening. So that makes it really easy. I could just load that. It's probably up in one file, and I could just load up that file and have a look through it and see where the error is, and then narrow it down from there. So it's going to make things much, much easier. One important thing to note about creating classes is that every class should have exactly one thing that it represents. This is called the single responsibility principle. And if a class kind of represents kind of 2 things at the same time, then that's your indicator, if you want to do a proper design, is to divide that up into separate classes. Again, smaller classes are easier to understand. And as a result, real-world applications typically are made up of relatively small classes. And each of those classes has typically very small functions inside. And so we usually subdivide our code reasonably small, not including comments and all that stuff, but we might have something like 20 lines of code in a function or less. And we might have something like 8 functions in a class or less. And as a result, we generally can understand our program much more easily. So anyway, I guess another advantage of object orientation is that the real world is object oriented. I mean, I'm an object right now. I hope that I'm performing the behavior instruct on you, which you're also an object. But maybe I'm performing the behavior bore on you, boring you. So it's possible. An auto mechanic might perform a repair behavior on another object, maybe your car. So anyway, the real world is naturally object-oriented, and it kind of comes naturally that we might implement a software system that's designed to simulate something real in an object-oriented way. It's usually something that people adapt to pretty quickly. Now, I don't care that much about UML, to be honest with you. I don't feel super strongly about it, but it is a way that we document classes in industry. I think that it's not a difficult concept. It's something that certainly high school students could learn. High school teachers normally prefer to teach more interesting topics to their students, and I understand that. Kind of agree as well. So anyway, but UML is actually really simple. So I'll just mention it in passing as we're going through. To represent a class in UML, all you have to do is create a rectangle and put the name of the class inside it. So here's 2 classes, student and course. Pretty simple, right? We'll build on this definition as we go, but it is relatively straightforward. One of the nice things about UML and documenting things in UML is that if you're new to a team, that team might give you a bunch of these documents that describe what the software looks like right now, or what they're working on to make the software look like. And they'll describe what all the classes are, and that's pretty handy because if you then are supposed to use these classes to do whatever it is you're implementing, you have a nice, compact, and very, it's not super detailed just enough to get you the information you need in order to use those classes. So it's kind of the right fit for documentation wise for somebody who's a programmer on the team to not constantly bother all the other members of the team and ask them, how do I use this function? You can just look at the documentation. And one of the ways that we document that is using UML, the Unified Modeling Language. All right, so data and behavior are combined together in a class. So the data in the class are called instance variables, or sometimes member variables. I usually don't use that terminology. So I'll usually call them instance variables. And they're called instance variables for a good reason. Even though we define them on the class, I mentioned before that classes and objects are a different thing. And I'm going to give you some help to try to figure out what are classes and what are objects, so we can get some practice with that. But remember that the class just defines that the instance variables exist. The individual instances of that class, or the objects in other words, they're going to have different values for these. So actually each object has their own copy of the instance variables. They're just sort of defined in the class, and the objects have their own copies of the instance variables. All right. Now, by the way, you might be wondering, well, what kinds of stuff can I have in my instance variables? You can have anything. So you can put basic types like ints and strings and so on. And also, in fact, your instance variables can actually have objects in them. So for example, I could have an order class, and instances of the order class will represent an order of a bunch of products that I wanted to buy off the website. And therefore, it might have a list of products that I bought. And products themselves would be objects. So it's going to be a list of objects. So that's totally possible as well. So just keep in mind that classes can have these relationships with one another in that their instance variables are actually meant to be of the type of another class. Or even you can have a class that has an instance variable of the same type as the class. So I guess sort of like recursion, but usually it's a much simpler concept to think about, where we might just have a linked list of things like products. For example, each product knows about the next product in the chain. So we have an instance variable called next or something, and it'll be a type product as well. So each product knows what the next product is. And class members also include behavior, and these are basically just functions. For some reason, we give them a different name when we attach them to classes. We call them methods, or sometimes member functions. Okay, but they are just functions. There are just a few little quirky differences, but for the most part, they're basically functions. So everything that we learned in the functions section is still going to apply here. There's just a few new concepts that are really straightforward. Okay, so let's first talk about instance variables. So first of all, let me just point out that instance variables are just another kind of scoped variable. So we learned about global variables. And remember that global variables are introduced not inside a function in a Python program, and they exist as long as the program is executing. So when they get declared, that variable hangs around until the end of the program. And then we also have local variables, and local variables exist until the function is done executing, like the return statement, for instance. So those are two scopes that we've seen before. Now we're introducing a new one. It's called an instance variable. And it's a part of an instance of a class. Every class defines the instance variables. Each instance or each object has their own instance variables that come into existence when the object is created. When the object no longer exists, then those instance variables go out of scope. Their lifetime is over. Okay? So that's really important to note. It's not really that different than a function, if you think about it. Local variables exist while the function is executing, and instance variables exist as long as the instance exists. If we delete the object, then the instance variables that are attached to that object go away. Some programming languages also have the concept of visibility. And what visibility means is, where can I access this variable? There's kind of something like that in local variables and global variables, if you remember. I was saying in the functions discussion that it's possible to have a global variable declared outside of a function, and then you can access it inside the function if you want to. But it's not possible for global code to access local variables that are inside a function. That's just not possible. There's no way to do that. And in fact, if we're not executing inside the function right now, then the local variable doesn't exist. That's not the case with instance variables, because the object could exist, but we might be executing code at a global level or code inside some other object. We're not necessarily executing code inside the object that has the instance variables right now. And so we can declare different types of visibility in order to keep track of who can access things and who cannot. So we have typically 3 different types of visibility. I'm just going to talk about 2 of them for simplicity today. I'll briefly mention the third one in the next section where we're talking about inheritance later in this lecture. But private and public. So basically what private means, if you have an instance variable that's private, the only place that you can access that instance variable is inside the methods of the class. Okay, so that means that an object can see its own instance variables that are private, but nobody else can. Okay, and that kind of makes sense. Private ensures that we have information hiding. And so I was mentioning before that that can be a huge advantage as far as maintenance of software, because we have some internal data structure that we're using to store something, such as the date of an order. And if we decide to change the data type that we use to store that data, if we have information hiding, it's a localized change in the order class, and we don't have to change anything anywhere else in the program. With hundreds of thousands of lines of code in your typical applications today, that's a huge advantage. And it could mean not only that there's a lot more code to change, but also that there are lingering bugs that don't end up getting caught because there's a very thorough testing process, and it may not be as rigorously applied when you make these subtle changes. So private variables can be really handy. Sometimes also you want your variable to be public. Now public means that you can see these instance variables, you can read and write the value from or to these instance variables inside the objects of the instances of the class, inside the methods basically of the class if you want. But you can also access them outside. So you can access them in methods of other classes or at the global level or anywhere else. So that's pretty handy. And then there's one more visibility, which is not mentioned here, which is protected, and that has to do with classes that are related to other classes. And so if you have a protected variable, it can be accessed by the object itself and also the methods that are in related classes. But only public can be seen outside of those related classes. We'll talk about the related classes later on in this lecture. So how do you access the class members? Well, imagine I have an object and it's in a variable. So let's say, for example, it's in a variable called sum_object. I use the dot, and then I give it the name of the member after the dot. So this one's a variable, as you can see here. So sum_object dot instance var name. Instance var name is the name of the variable, and I'm just assigning it a value 7. So here I'm writing the value, but you can also read it the same way. So for example, if I say sum_object dot instance var name, that's a number. That's going to be the same as 7, and I can use it inside a mathematical expression. I could pass it as an argument to a function or whatever. So the dot. When I read through code, I usually, when I see the dot, in my head, I always have these English equivalents to what I'm reading. And so in this case, I'm saying sum_objects member instance var name. Okay, so the dot kind of means member in my brain anyway. All right, so if you want to add instance variables, then the UML diagram changes to have a second rectangle. Ooh, it's very advanced, this UML technology. It's 2 rectangle technology. So here we've got 2 classes, student and course, and I've just added a couple of variables to each one. So maybe students have GPA and a list of courses and a list of grades. And courses have a name and a code. Okay, and so all we do is in the top rectangle, we put the name of the class. It's usually a little bit bigger. And then in the bottom rectangle, we put the instance variable names and types. And we usually use this syntax that actually is familiar to us Python programmers, but a little bit strange to a C++ or Java programmer. We use the name, colon, and then the type. Now, the types here don't match the way that they're supposed to look in Python. They are quite similar to what they look like in Java, and you'll find some variation here. There isn't really a strict rule about what the types should look like. They don't have to correspond to types in a very specific programming language at all, but you should be able to figure out which types you should choose. So if I was looking at this diagram and I wanted to implement these 2 classes in Python, I'd say, oh, okay, so GPA is supposed to be a float. Well, Python actually has a type called float. And then I say courses needs to be a list of course. I'd say, okay, well, Python actually has a built-in type called list, and I can just populate that list with instances of course, which is the other class. That's one of my own types. And then a list of string in this case, Python would represent this as lowercase list, square bracket str, lowercase s str. But this is pretty straightforward how I would implement this in Python. So it's important that these types are specific enough so that you know how to implement them in different programming languages, and hopefully not too specific so that they only kind of are relevant for one specific programming language. Okay, so next let's talk about the behavior side of things. So behavior basically just functions. When you have methods again are just functions that are part of a class. When you execute those methods, they can access the instance variables of that instance. So whatever instance you're running the method on, it has instance variables, and you can read and write those instance variables from inside the methods of that class, whatever class the instance is an instance of. Okay, so that's important to note. Otherwise, instance variables would be pretty useless because we couldn't access them from anywhere. I was mentioning before, we have private instance variables that are only accessible inside the methods of a class. So obviously you can access the instance variable, the private instance variables from inside methods. You can also access the public ones. Public ones are visible everywhere. All right, so methods also have visibility, and the visibilities are the same. So we have private methods, which are only supposed to be executable from inside the class. So you can call the function from another function, another method in the class. And you can have public ones that can be called from outside of the class. And there's also a protected one, which doesn't allow you to access outside the class, but only inside the class or inside a class that's related to the current class. So those are the visibilities. Here's the bad news. Python doesn't really have the concept of visibility. Maybe it's good news because then you don't have to worry about it. But in a lot of programming languages you do, so I'm mentioning it so that you understand object-oriented programming for your C++ classes or Java or whatever, because there is such thing as private, public, and protected for C++ and Java. But it doesn't exist in Python. In Python, like a lot of other things, just like type hints that we were talking about in the functions demo, type hints are useful and they make it easier for you as a programmer because they can give hints. It isn't required that you abide by the rules of public, private, and protected in Python. So it doesn't enforce these rules. But what the convention is that if you want to have a private instance variable or a private method, what you do is you put an underscore at the beginning of the name. Okay, and again, it doesn't mean anything. Like Python's not going to stop you from calling a function that has an underscore at the beginning out from outside of the class, but it should be a clue to you so that maybe I'm not doing the right thing here if I'm trying to call a function that I clearly wanted to be private, or whoever wrote this code clearly wanted this to be private. It's probably supposed to be accessed from another function that isn't private. So that's something to keep in mind. Those are called under functions, by the way. Under is just short for underscore when you see an underscore in a function. There. We'll get into the Python details in a minute. So just like when I wanted to access an instance variable, use a dot in order to call methods. So SumObject dot method name is actually a function. And so I can call it just like I call any other function. So SumObject dot method name, round bracket, and then some arguments is actually going to call method name on the object SumObject. If it helps, you can think of SumObject as being like a third argument to this function, because the SumObject actually does have access to SumObject itself. It has access to arg1 and arg2 in this case, but also SumObject. So if there are instance variables on SumObject, the method can access them. So I like to think of these three as being all three of the arguments. In programming languages like Java and C++, this is just sort of a helpful tool for you to understand that it's kind of implicitly there's kind of a third argument whenever you call a method. But in Python, it's a bit more explicit than that, because when you define a method, you always include an argument called self, which represents the object that we're calling the method on. So it's actually much easier to remember this concept in Python because we do it more explicitly. All right, if you define methods in your class, then guess what? You have to use 3-rectangle technology. I know, humans can't perceive more than 3 rectangles, so don't worry, we're going to stop here at 3 rectangles. So here we have 2 classes, and they have 3 stacked rectangles. The top one, slightly bigger font, has the class name, usually centered. And the second one has the instance variables and their types. And the bottom one has the functions, including types for the arguments and return values if there are any. Anyway, in this case, I left off the return value for a set course grade here because this is a really long function. If you include all of the argument types and the name of the function, it becomes really big, and just to fit it in, I didn't bother putting it in, but I'll show you here. You could put :none if there's no return value, or you could say :void. Kind of people choose things that are a little closer to their own programming languages. So void's what you'd see in Java and C++, and none is what you'd see in Python. So I'm using the Python. So I guess I could use str, I suppose. I've seen a lot of UML diagrams, and things like float and the whole word string are typically used, so I'm sticking to that convention. So anyway, UML is pretty straightforward, and you can see how this would be immediately beneficial, because if I know that somebody wrote a course class, I could download the course class and read through the hundreds of lines of code, or I could just look at this diagram and say, oh look, there's 4 functions. One called setName, and it takes a name. And there's also one called getName that returns a string. I bet I know what it does. It returns the name. So it's pretty straightforward to understand what these functions do if the names were chosen wisely. And so maybe this is all I need in order to start using the course class. If I need more than that, then I might need to look at the source code, but this can be a really good shortcut. So let's talk about how to implement classes in Python. So classes are the fundamental. We're going to want to take the classes and define what data, what behaviors are there, and also we want to then instantiate the classes, which basically means make an object instance out of the class. So let's figure out how that goes. So here's our first class. So we're going to use a keyword class, very much like the def keyword when we're defining a function. We use the keyword class. Then we give it a name. Now, it's customary for me to use a capital letter when I'm defining classes. There are some people who use lowercase letters when they're defining classes, in particular in C++. A lot of people use a lowercase letter for their C++ classes. I believe in Python it's standard to use a capital letter for your class names. And if you need more than one word for your class name, you'll still use snake case, except you'll capitalize all of the words. So maybe this was something like, international student would be something like capital I international underscore capital S student. And you can see that the contents of the student class are, in this case, are just two functions. We actually literally use the keyword def to create the two functions. There's a function called getAverage, and there's a function called setCourseGrade. And notice the thing that they both have in common is that they have an argument called self. The first argument, the only argument in the case of the getAverage function, is called self. And this is a built-in, automatic, should always be there argument for every single method. Okay, and the reason why we need to include it is if I want to access the instance variables, the way that I do that is I use self dot to access them. So here I'm accessing some kind of an instance variable called average that maybe was calculated down in this function. And so average is here, so I say self dot average. If I didn't have a self variable, how would I access average? Well, in some other programming language, there's an implicit variable. They usually call it this instead of self. Like in C++, for example, there just is a variable called this. It's not declared anywhere. You just have to know that it exists, and that's true in Java and JavaScript and so on as well. But in Python, there isn't such thing as this. And in fact, if you want to use self inside your method, you have to have self in the argument list. And whenever you call, let's say, for example, I create a student called Bob, and then I say bob.getAverage. Bob gets put into the self variable when getAverage is called. So if I ever call bob.something, I had better have an argument to store Bob. So there has to be an argument, and it's just called self in Python. All right. None of the code of this function is really important. It's code that we've seen before, so we can just skip that. How do you instantiate a class? Well, let's say, for example, I have a class student and a class called course. I didn't show you the course class yet, but I will show you later. But I can just create a new instance of the student class by literally just using it as if it were a function. So it kind of looks weird. But because I used a capital letter in the name of my class, it's obvious to me anyway that I'm not actually calling a function, but what I'm actually doing is I'm instantiating a class. Fancy word for saying I'm creating an object from a class. And that object, then, which is an instance of student, gets put into a variable called Liza. Now, Liza is actually a variable which points to the memory location, just like we've seen with other variables. It points to the memory location of that student instance somewhere. Okay, and in fact, objects are just like lists and dictionaries. When we call functions, they are passed by reference. So this is called a reference. So Liza is a reference to that instance of student. So don't think of Liza and the actual instance as being the same thing necessarily. Liza is sort of a variable that points to where that student is. That's not super duper important, but when you write a function, it's important to note the side effect of that is that it's going to be passed by reference. So if I change Liza, or if I change the student instance inside a function, Liza will also reflect those same changes because it was passed by reference. So anyway, here I actually create an instance of Liza, a student called Liza, and I create an instance of course called intro.cs. I call a method on intro.cs. There's a method called setName, and I pass it a string, introduction to computer science. And then I say Liza.setCourseGrade, intro.cs, and then some number. So presumably this is Liza's grade in the intro.cs class. And so I'm just passing these two arguments into a function. So notice here I'm actually calling a function on Liza, and I'm passing as an argument a different object, an object of a different class. Okay. So classes have a concept of a constructor. Now, none of the code that I just showed you used the constructor, so I'm going to introduce it now, and then from now on, we'll use code that uses a constructor. A constructor isn't really a good name because what it kind of makes you think about if you think of constructor is it's used to create the instance. But the constructor doesn't create the instance. What it does is it initializes it. So basically, when you have code like this right here, where Liza equals student, the first thing that happens is Python reserves memory for all of the instance variables that student defines. Okay, so it sets aside a little bit of memory, and it makes a reference from the Liza variable to that memory, and then it tries to initialize that memory. So all of the instance variables, they need initial values. That's what the constructor is for. So it doesn't construct, it actually initializes. So it should be called the initializer, but it's a pretty old term, so it goes back to like the 1960s. And so we're kind of stuck with the word constructor. But one thing I like about Python is Python's constructor actually called init. Well, technically they're called underscore underscore init underscore underscore. And so this is both good and bad. Number one, it's good that it's called init because it doesn't sort of say constructor or anything like that. Some other programming languages are quite confusing because people, newbies to object-oriented programming, think that it's a constructor. It creates the object, but it doesn't actually. The object's kind of created behind the scenes, and then an empty object is handed to the init function, and the init function, I'm just going to call it the init function to keep things simple. The init function is going to initialize all of the instance variables in that newly created instance. Now, the bad thing about this is that Python insists on using these double underscores at the beginning and the end. From now on, I'm going to refer to these as Dunder functions. That's what they're called in Python circles, because it's a double underscore. Okay, so we usually say Dunder init is the short form for this, which is a handy way of saying something like saying underscore underscore init underscore underscore is quite a mouthful. All right, so Dunder init is a function whose purpose is to initialize the instance variables of a newly created object. All right, and it doesn't return any value because it's kind of built in. You don't call it directly. It's kind of implicitly called. So going back to here, I'm actually calling Dunder init, even though I don't notice here. I'm calling Dunder init on student here to initialize whatever is built into student, like their GPA and their name and so on. Okay. Now you can actually have a Dunder init function that takes arguments. So for example, if you want to initialize your object with some initial data, instead of just giving it empty values for its initialization, you can give them some starter values. Another built-in function, so just this is common for all built-in, so you got to get used to it, the Dunder syntax. So Dunder str is an example of another built-in function. And what the str function is, or the Dunder str function, is used whenever we call the str function, like str, not Dunder str, on an object. So we've done this before. So for example, I might have had something like a string that contains the word Sally, the name Sally, and then an integer, and I want to stick the 8, the integer, at the end of Sally, but I can't do that because you can't add a string and integer together. So I use the str function to convert the 8 to a string equivalent, and then I can concatenate them together because they're both strings. Well, determining how an object converts into a string is actually determined by the Dunder str function, which is a function that you can write. So if you want to determine how your class, let's say you're making a class called product for Amazon, you can write a Dunder str function that takes your object, your instance, and converts it into a string representation. So it's pretty handy. For example, whenever you call print and you pass it a non-string variable, what Python does is it looks to see if that object has an str function, like a Dunder str function. And if it does, it calls that function in order to get a string representation of the object. Now you can put whatever data you want into that string. That's up to you. But it's very useful when you're debugging because you might want to print out an object, and hopefully your Dunder str function will put the correct data into that string so they can see which string is it, which product was it that I'm checking at this point. Does it have the right price and the right description and so on? All right. So here's an example. This is spread across 2 slides because the code is a little bit long. So here we've got the quote-unquote constructor, the Dunder init function. And you can see that I've got a self argument, which you're always going to have in every single method, including the built-ins and the non-built-ins. So we're always going to have self, and it's always the first one, by the way. But I've decided to add 2 more arguments to it so that when I create my course, I'm going to pass 2 arguments inside the brackets. When I say course bracket, I'm going to include a code, and then comma, and then a name. And then the code is just going to automatically be put into the instance variable code. So see the difference here? This code here is a local variable defined by this argument. And this variable, self.code, even though they have almost the same name, self.code refers to the instance variable because I'm saying code is a member of self. That's what the dot means, remember. So this is storing the argument value code into the instance variable code, and then it's storing the argument name into the instance variable name. And sometimes we might, for these variables, we might create get and set functions. So get code, for example, might just return the value of code. So I could actually just access it by saying, intro to CS dot code. I can access the instance variable directly in Python, but it's not using information hiding if I do that. So if I want to be proper and to avoid potential headaches by accessing data directly like we've talked about before, I can create a get and a set function for that. Get functions are also called accessors sometimes because they let you access the value that's otherwise hidden. And then there's also set functions, which are sometimes called mutators. Mutator just means to change. So mutator is a object that changes the value of a variable. And it takes a second argument here, which is the new code, and it overwrites the instance variable's code value with the argument code. So these are getters and setters, sometimes informally referred to. They're referred to as getters and setters, or accessors and mutators if you're in class or you're talking to an interviewer or something. Okay, and then there's a couple more. So there's also a get name and a set name function. I don't think we need to talk about those because that serves the same purpose as get code and set code. And then there's a dunder str function. And so the dunder str function only takes the self argument. I have no control over the arguments of str because it's built in. And here I'm just using concatenation. I guess I wrote this slide before f strings became a thing. And so what it does is it takes the code of the course, which is some numeric code, but it's a string. And then I concatenate that with a space and then an opening bracket. And I concatenate that with the name of the course, and then I concatenate that with a closing bracket. So it's basically going to be course code, space, and then in brackets, course name. So that might be a pretty good str conversion function that I could use. And you can see that you could obviously use an f string here. You could if you had if you wanted to create a dunder str function to represent a Pokemon, you could list all of their moves and their stats and things like that. So it doesn't have to be one line of code, but it's usually a pretty simple function that allows you to see the contents of an object when you print it, or when you convert it to a string generally. All right, so here I'm going to use that newly created init. So going back here, we have the init here, and we have 3 arguments, self, code, and name. Now self is going to be the built-in object that's being created for me, so I don't supply that. So I actually only supply 2 arguments to this course here. First is the course code. Second is the name of the course. And then here's another biology course, and it has this course code, and this is the course name. And those are being passed in as the code and name arguments of the dunder init function. Okay. All right, so that's the basics of classes. They're pretty straightforward, and we'll do some examples, obviously, so you get the hang of the syntax. But knowing functions actually makes developing classes significantly easier because the vast majority of what a class is what functions it has. But one concept that classes allow us to do that doesn't really exist in functions is the nature, the concept of inheritance. It allows us to have classes that are related to one another. Classes can be related in different ways, and inheritance is only one of the relationships that are possible. We talked about one relationship already, a different one, where I could have a class that has an instance variable. The type of that instance variable is some other class. That's a relationship that's possible, but inheritance is a different relationship. Now, inheritance means other things out in the real world, so make sure that you pay attention that the definition of inheritance is a little different. We're not talking about inheriting money from your rich aunt. We're not talking about inheriting genes or whatever from your biological parents. What we're talking about here is where we're going to have classes that inherit behaviors from another class. So that way we don't have to define those behaviors again and again on really similar looking classes. We can just define a class that builds on top of another class. Okay, so first let's try to get the idea of what inheritance is and what it isn't. This is really important. So there are a lot of terms that are used if you read books about inheritance that you'll see. I kind of have a fairly comprehensive, but probably not completely comprehensive. Imagine I have a class B and another class A that has some functionality that I want to borrow. So one way that I could borrow the functionality from A is I could just copy and paste it from the A class into the B class. The reason why we don't typically do that is because now I need to maintain both of those two snippets of code. If there turned out to be a bug in A, I got to go back and change B as well. And if I end up copying and pasting many times, this can be very much a headache, and I'm very likely to miss some of those examples. And it's going to be frustrating and unfun for me to do anyway. So it's nice to have a built-in feature to allow us to take some of the things that are provided in another class and use them in our class. So inheritance is the way that we do that. So first you want to ask yourself, is the relationship here between these two classes, is it inheritance? And here's the way that you do that. So first of all, what does it mean? When B inherits from A, it says that's the same as saying B is A. That's the phrase that I like the best. Okay, so an example is car is a vehicle. So if I have a class called vehicle and it defines things that vehicles have, so vehicles typically have, a power source, they have seats, they have, energy levels like gas or battery power or whatever. And then cars are just more specific versions of that. So they have wheels, that's how they get around, engine specifically, and their power source might be, electric battery, or might be a gas tank or a propane tank or natural gas or whatever. So a vehicle certainly is a generalization of a car, and a car is a more specific version of a vehicle. So to put all the terminology aside, let's just say that B is a specialization of A. That just means that B is more specific. A car is more specific than a vehicle. And A is a generalization of B. In other words, a vehicle is more general than a car, because a vehicle also includes, a submarine and an airplane and so on. And you could also say A is the parent class. So this is where it gets a little confusing, because I was saying before, it doesn't have anything to do with inheriting wealth or inheriting genes from your biological parents. But we do actually use the term parent class. So A is the parent class, and B is the child class. So we do actually see that sometimes. Another way of saying that is to say that A is a superclass of B, and B is a subclass of B. Super and sub just mean above or below. And so A is above B in the hierarchy. In other words, like going from most general at the top to most specific down at the bottom. A is above and B is below. All right, so this is really, really important, because this is going to be what you use to determine if inheritance is the right relationship. Okay? So here's an example. Let's take an example class. Let's say, for example, our school offers courses, and let's say there's some kind of a global pandemic, hypothetically, and they decide to create some online courses. So in order to implement this online course, your job as the software developer is to create the functionality necessary to make the online class work. And we kind of want it to work in the same general way as the course works. So what we're going to do is we're going to inherit and reuse the functionality that's provided with course. There's no reason to rewrite it. So what we'll do is we'll say that online course is going to be a subclass of course. Course is the superclass, online course is the subclass. So a course is more general, right? Because an online course is a very specific kind of course, And there are other kinds of courses that aren't online courses. So we say that course is a generalization of online course, and perhaps more usefully, online course is a specialization of course. It's a really specific kind of course. So online course might have some stuff that's unique, like a web address, for example. An online course is usually hosted on some kind of a web platform. So maybe we have a web address where we can visit the lectures, maybe a different web address where we can complete assignments or whatever. We might have a Boolean value that says whether or not it's open or closed to the public. Some prestigious universities release some of their material open to the public, and I've been trying to do that at this university for a while. It's the purpose of this YouTube channel. But generally speaking, it isn't in widespread adoption to do that. But lots of universities have some courses that are closed and some courses that are open. I don't think any universities have completely open courses. All right, but online course still needs all the stuff that comes from course. So like names and codes and all that stuff. That was a really simple class, so we're not really inheriting that much, just 4 lines of code or whatever. I guess we had all the get and set functions for the get code and get name and set name. But it wasn't really that much code. So we're going to save ourselves like 12 lines of code by using this inheritance. But hopefully you can understand that courses are usually pretty complex, and we put a lot of time into developing them and make some advanced algorithms and potentially make errors in doing so. And as a result, when I finally debug that program, let's just reuse it so I don't accidentally have to go through and make all of those same errors again and fix them all again. Okay, so here's an example of an inherited class. So this is mostly the same as what we've seen with the course class, but you can see a couple of key differences here. So we say class and then the name of the class. Then we have this round bracketed expression, which we didn't see before. This is describing what the parent class is. So I'm saying, I want to create a new class, online course, but this is going to be a subclass of course. Okay, so online course is a subclass of course. What that means is I have access to all of the functions that were defined in course now. And then we have a dunder init function. And notice that it's self-code name. It takes the same 3 arguments as the course dunder init function does. So what's kind of cool about that is I can actually call the course's dunder init function. And here's what I'm doing right here. So I say super, round bracket, and what that does is that's giving me the super class. That's where the name comes from. So super round brackets is a function that I can call that gives me the super class. And then I literally just put in the name of the function that I want to call. I want to call init, or dunder init. And then I pass it the 3 arguments that we just got. But in addition to passing these two initialization variables along, I also want to initialize 2 more variables. I'm just going to put hard-coded values in this case, but I could have another argument here, such as web address, and then I would set self.webaddress equal to web address here. That would work fine. And we'll do an example like that in the demo. So here I just set web address to an empty string, and I set one called open to public, and I'll set it to false by default. And we can change it using some of the functions. So then we create some getter setter functions, or accessor mutators if you're more formal. So we have a get web address, which just returns the web address. We have a set web address, which just overwrites the web address with a new web address. This is really important because we actually just set it to blank string, which is not going to be very useful. So we have to be able to set it at some point. So we usually have 2 options when we're creating a new class. Give the person who's creating the class, the instance, a constructor that takes the data as argument to initialize it, or provide a set function to allow you to override it, and oftentimes we do both. So in this case, I didn't do both. I only have a set function. Now notice that the getter for the Boolean valued variable actually starts with is instead of get, and that just makes it more readable. This is my convention, and it actually is used by a lot of coders, but a lot of coders also use get. So get open to the public isn't wrong, but is open to the public is a more English sentence. So oftentimes you might do something like if statement is open to the public. So if it's open to the public, I mean, that's just really easy to understand. So I might have a variable called intro to CS, and I'll say something like if intro to CS dot is open to the public. That's just very understandable. It reads like English, and as a result, that's why I name my function this way. And the functions can be called whatever you want, so you might as well pick something that's readable. There's also a set function which overrides the value. So this only works for Boolean values because you're asking a yes or no question kind of when you call that function. All right, so if you want to represent inheritance UML, you break out new technology. I did say, 3 rectangles is the maximum that humans can understand, but we can add in a triangle. So imagine that we add in a triangle arrow. Just keep in mind, this is a quirk about UML. It's not my personal preference or anything. The arrowhead has to be a triangle. Okay, so if you want to just do the V-shaped arrowhead, that actually means something different in UML. So make sure you choose the correct arrowhead. It has to be a filled triangle, like you see here. So that's a little bit strange. But this diagram here just means that an online course has a function called set web address, get web address, set open to the public is open to the public. But it also inherits the get name, set name, get code, set code functions from its parent class course. So that's pretty cool. And of course, that means also that we have access to the instance variable. So online course has a web address and an open to a public instance variable, but it also inherits name and code instance variables from course. However, in some programming languages, because you can set instance variables to private, imagine if name and code were private, well, an online course couldn't access name or code directly. It could only access it through the get name and the get code and set code functions here. So that's something to note. That's why the visibility of protected exists. Protected means that if I'm a subclass, or even if I'm a subclass of a subclass or somewhere down the descendant trail of courses, I can still access all the instance variables all the way up the ancestor hierarchy. Okay, so how do you instantiate a class that is a subclass? Well, one of the important things to note is that an online course is a course. Remember that phrase that I told you about? That's what you can use to verify that things actually are inheritance relationships. So, for example, if I ask you, is a car, or if I were to say, a car is a vehicle, that's a sensible statement. And so it makes sense. That's something you could say, and somebody would agree with it. So therefore, it kind of confirms to me that car and vehicle have an inheritance relationship. On the other hand, you could say wheel and car. And if you ask yourself, does wheel have an inheritance relationship with car? It's hard to answer. But if you say a wheel is a car, that sounds like nonsense. And so it's pretty clear that the relationship between wheel and car is not inheritance. It's some other relationship. You might say something like, a wheel is a part of a car, or a car has a wheel. That's different, okay? So is-a is what represents inheritance. So ask yourself the is-a word if you're ever trying to confirm something is inheritance. That's true in this case. An online course is a course, right? And since we're saying that, I should just point out that wherever I could use a course, I can use an online course, because an online course is a course. Not all courses are online courses, but all online courses are courses. And so, for instance, remember we had this function called student.setCourseGrade, and it took 2 arguments. One was a course, and the other one was a mark. Well, now actually I can supply an online course as that argument. Because an online course is a course, this is perfectly allowable. Anyway, so that's a pretty important point that I want to bring up. And this is, of course, true because of the relationships between these classes. You can't just create any old class, even if some of the functions are similarly named. You can't just create any old class and then just swap them out for one another. They have to have this relationship. You can substitute a child course or a subclass in for a parent class, but not the other way around. All right, so let's do a quick. So here's a really simple example where we have 2 classes using inheritance. So let's just go over these 2 classes really quickly. I made them small so that I could fit both of them on the screen at the same time, along with some code to use it, the driver code down at the bottom. So lines 1, 2, 3, 4, and 5 define a class called animal. It has a Dunder init function, which takes 2 arguments. Of course, we always include self, but it includes one more argument, name. So when I declare a new instance of animal, I'm going to pass a name to it. Okay, so that's one important thing to note. And all it does with that name is it stores it in an instance variable by putting it into self.name. That's the instance variable. It also defines a function called eat, which only takes the self argument. All methods must take the self argument, but there's no other arguments here. And the only thing that eat function does is it prints the name followed by the word eats in a period. Okay, so relatively straightforward. And then we have a subclass called lion. And you can see that lion inherits from animal with the round brackets there. We also have a Dunder init function, which also takes a name variable. And you can see we're just setting the name to the instance variable. Equivalently, I could have called super.dunderInit here and passed the name, the self and the name parameters to it. But all that would mean is that the Dunder init function on animal would be called, which would store the name into an instance variable self.name. And we are doing that directly here. So it doesn't really matter. You can choose one or the other. It's probably better to use the super.dunderInit, but this really simple example would be fine. The lion class also has a roar function, which just prints the name and then roars, exclamation mark. And then the driver code down at the bottom creates a new variable called nala, and it is going to create an instance of lion. Because lion is the subclass, I'm trying to instantiate lion, and I pass one argument to it, the string nala with a capital N. Now that nala gets passed to the Dunder init function, and the nala variable with the lowercase n here, that is what we're going to see in the self argument of the Dunder init function. So the self contains the object, and name contains the string nala. So then on the object, on nala, we're going to create a new instance variable called name. We're going to set it equal to the string nala. All right, so that's what line 11 does. So we're now going to have a lion. It's going to have all of the stuff that both lion and animal both have. And then we're going to call nala.roar and nala.eat. And it's going to call the roar and the eat function. So it's going to print out, nala roars and then nala eats. But let's actually see how Python figures out how to call these functions. Okay, because the roar function is defined on the lion class, which is more directly what kind of object nala is, but eat is not. So when we first run this code, it's going to create an instance of lion somewhere in memory. I'm not displaying memory here just for simplicity. This is a UML diagram showing the structure of the classes. You can see we have an animal class and we have a lion class. This one also shows another subclass of cow, just to show you that you don't have to have just a class that has one subclass. You can have many subclasses. So for example, there are different types of animals. A lion is an animal, so this is a valid inheritance relationship, but a cow is also an animal, so we could say a cow. And you can see they define some behavior that's different. So a lion has a roar function and a cow has a moo function, but they both have an eat function. Right? And I've decided to keep them as simple as possible, no arguments and no return values. But anyway, okay, so there we are. So you can see now, anyway, we're on line 12 and we're trying to call the roar function. Well, nala actually is a lion. So it's on the direct class that instantiated nala in the first place. So if I want to figure out how to run roar, I just start looking at lion and I find it right away. There it is. There's the roar function. So we just execute it directly. It's on the lion class. It's a little bit less obvious what happens in the case where we want to call eat. Okay, but the process starts the same way. So what we're going to do is when we call the eat function, we're first going to look on the lion class. Is there an eat function there? Well, it turns out there isn't one. So the next thing we do is we go up the hierarchy and we look for the eat function. If it turns out there was an eat function that we executed, if not, we might even go up higher because you can have, subclasses of subclasses of subclasses. You can create this big giant hierarchy. And all we need to do when we're searching for a function to call is go up the chain, work our way toward the top level. All right, so hopefully this example helps you understand a little bit about how functions are executed in an inheritance situation. Animation demo. All right, so that's it anyway. Hopefully this was pretty reasonable to understand. Again, it's going to take some practice, obviously, but this is a really good start. So see you next time.